I have one simple request, and that is to have
Cessnas with frickin' laser beams
attached to their heads.
What you're seeing here is the first version of a remotely piloted aircraft. We've retrofitted a Quad City Challenger 2 ultralight with our hardware and software and successfully demonstrated automated taxiing, takeoff, and landing. Now it's time to move to version 2, and we've chosen the Cessna 150 as our next platform to modify. In this episode, we're using a laser scanner to create a detailed 3D model of the aircraft, a crucial step for designing our autopilot installation. The equipment we'll be using today is the HandyScan 3D by Creaform. At an insane cost of $100,000, 3D scanner consists of 3 parts: a laser head, a computer, and the software that reads and stitches the scan. The scanner takes 1.3 million measurements a second, each with an accuracy about the width of 2 human hairs. This data gets sent to a computer, and using special software, we're able to combine the measurements and visualize our part. Today, we'll create a model of the instrument panel, rear cabin, strut, top of the fuselage, and the first part of the tail cone section. But unless we have a box of stickers, we're going to fail. Here's why. You are located on this street corner. Without giving prior information of your location, you could perceive that you are located here, here, or here because all the streets look identical. Unless we add variability. Curved streets, buildings, trees, all these features help you locate yourself within your environment. The 3D scanner uses a similar concept to locate itself in 3-dimensional space using randomly placed reflective stickers. With the scanning head's known position and the distance measured by the laser, the software is able to fuse the data to recreate a virtual representation of the part. On the instrument panel, we had to take extra precaution by adding strips of tape with reflective markers over the large panel gaps to prevent the scanning head from losing its location. Additionally, as we scanned around the strut, there were brief moments where not enough markers were in sight for the scanner to know where it is. Fortunately, adding more reflective markers is an easy fix. We finished scanning the plane, but our challenges aren't over. Planes are kind of a funny shape. We've got random curves, edges, and flat surfaces with no obvious physical reference for the location of the center line of the aircraft and the 2 other axes. This is important because when we start designing parts, we may want the orientation to be aligned with the axes of the aircraft. For instance, if we mount a payload on the strut, wink wink, we don't want it to be crooked. Solving this problem takes a bit of creativity and making some assumptions. For the scan of the strut, we assumed that the pitot tube was aligned with the free stream air during the cruise configuration, meaning that if we were to use it to define the axis that aligns with the front and the back of the aircraft, there's a good chance that a payload hanging off the strut will look straight when flying. Then, we assume that the rivet seam running along the spar is what defines the axis running from one wingtip to the other. In the rear cabin section, we solved this problem in a different way. While looking through an inspection panel on the floor, we found the landing gear attached to a big piece of cast aluminum with 2 inclined planes. On the computer, we're able to click on the surface representing those locations, and the software gives us a measurement of how flat the surface is. If flat enough, we're confident we can use it as reference. Indeed it was, so we assume that the intersection line between those 2 inclined planes would define the center of the aircraft. The last part required to create a nice model is to remove the features that aren't essential. The instrument panel is a good example of a scan needing a good cleanup. See how there are many wires behind the panel and knobs that we would rather not have there. The software allows us to remove these components and we're left with a nice final product. This is a side-by-side comparison of the part and then the scan. Here's another one. And here's another one. To see us design the instrument panel in the next episode, subscribe.